All right, let's talk about something that's kind of weird in the world of AI. We've got these models that are so powerful. They can write poetry, they can code, they can crush exams. But what happens when you give them a really long, really dense document to read? Well, that's where things get messy and start to fall apart. And we're going to get into exactly why.
So, yeah, this is the big question, right? It just doesn't feel right. How can a model that gets the subtleties of human language get totally, completely lost in something like a merger agreement? The problem, as you're about to see, isn't just about the number of words, it's about how all those words connect to each other. This gets us to what's called the long context trap. And the issue here is way more subtle than just saying a document is too long. We're actually dealing with a very specific, very frustrating kind of failure that researchers have given a name to. And that name is context rot. Think of it like this. You've got this brilliant assistant, right? You give them one book to read, they know it inside and out. But the second you give them another book, they kind of forget everything from the first one. That, in a nutshell, is context rot. The more stuff you try to cram into the model, the worse it gets, especially if you're asking it to remember and connect tiny details from all over the place. See, the thing about context rot is that it's not just one problem, it's two. You've got context length on one side, that's just the sheer amount of information. But then you have task complexity, and that's all about how interconnected that information is. A legal contract isn't just a long story you read from front to back. It's a web, a maze of clauses that all point back and forth to each other. And that interconnectedness, that's what really breaks these models. And let's be super clear here, we're actually pretty good at solving the simple needle in a haystack problem. Finding one specific fact in a huge pile of text. That's just retrieval. The real monster we're fighting is something called multihop reasoning. This is where the model has to find one clue, think about it, then use what it learned to go find the next clue, and so on. And what researchers have found is that as soon as you ask for more than just a couple of these hops, the model's performance just falls off a cliff.
So you might be wondering, okay, so what if people tried? Well, the usual workarounds that everyone uses have all turned out to be, well, pretty flawed, especially when you throw real-world complexity at them. First up, you've got the brute force method. Just stuff all the context you can into the model. This is super expensive, it's slow, and like we just saw, it actually makes context rot worse by adding a ton of noise. Then there's summarization. The issue here is that summaries are, by their nature, lossy. You lose critical details, and the model starts to drift off and get the wrong idea. And finally, you have RAG, Retrieval Augmented Generation. It's great for plucking out simple facts, but it's brittle. It's basically just a fancy keyword search, and it completely fails to understand the complex logical links you need for that multi-hop reasoning. Okay, so if all the usual tricks are failing, what's left? Well, it turns out we need to just fundamentally change how we think about these documents in the first place. So instead of treating a legal contract or a huge code base like a storybook that you just read from page 1 to the end, we need to see it for what it actually is, a dependency graph. It's a network. It's got nodes like different clauses or functions and edges that connect them all. And once you start thinking about it this way, a whole new world of solutions opens up. And that new way of thinking, it leads us to our first huge breakthrough, a real architectural fix from some brilliant researchers at MIT. It's called Recursive Language Models, or RLM for short. The big idea behind RLM is a total paradigm shift. Instead of trying to cram the massive document into the model's memory, you treat the document as an external environment. The model doesn't have to memorize a single thing. It just has to learn how to move around inside that environment using code. And it does this using a really simple but incredibly powerful loop. First, it reads a little bit of info about the document. Then it evaluates what it sees by writing and running some Python code to search for what it needs. Next, it prints the result of that code back to itself, and then it just loops, doing it all over again. It can even call up smaller, specialized models to handle little subtasks. This is exactly how it builds and explores that dependency graph we were just talking about. And the results? Just look at this chart. It's night and day. You can see the standard model's performance just tanking as the context gets longer. But the recursive language model, it just cruises along with incredibly high accuracy, even when you feed it documents 100 times bigger than what the base model can handle. It's a massive leap forward. All right, let's totally switch gears. We've seen the big, impressive architectural solution. Now let's look at something completely different. This isn't some complex new framework. It's a fix that is so simple, it honestly sounds like a joke. But it targets a deep, fundamental flaw in almost every large language model out there. And this quote just captures it perfectly. Seriously, what if the secret to unlocking way better performance was just
copying and pasting your prompt twice? It sounds ridiculous, I know, but it works. And it's called prompt repetition, or RE2.
Okay, so to get why this works, you have to understand this flaw called causal masking. Basically, when an LLM reads your prompt, it's like it's driving down a one-way street. It is literally architecturally incapable of seeing the end of the prompt while it's still processing the beginning. This creates what researchers call a triangular prison for its attention. So if your most important instruction is at the very end, the beginning of your prompt never even knows it exists. RE2 is basically the key that unlocks that prison door. When you paste the prompt in twice, that first copy acts like a read-only memory, like a virtual scratchpad. Now, when the model starts processing the second copy, every single word in it can look back and see every single word in the first copy. This effectively simulates perfect two-way attention and totally fixes the model's vision problem.
And the impact of this simple little hack is just staggering. On a classic needle-in-a-haystack test, a standard model scored a measly 21.3% accuracy. With RE2, literally just by pasting the prompt twice, that accuracy shot up to an incredible 97.3%. That's almost a five-fold improvement, which is just wild.
And this wasn't some lucky fluke. RE2 gives you consistent improvements across a whole bunch of different models. In 70 separate experiments, it made things better 47 times. And it never, not once, made things worse. It's what you'd call a pure win in AI research. And the best part? There's no performance hit because you're just adding fast input tokens, not the slow output tokens that actually cost you time.
Okay, so where does all this leave us? What's the big takeaway? We now have two really powerful but really different tools in our toolbox to fight this long context problem. The trick is knowing which tool to use and when.
So here's the simple playbook. If your problem is full of deep complexity and requires that multi-hop reasoning, like trying to analyze a legal contract, then RLM is your best friend. It's built from the ground up to navigate that kind of dependency graph. But if your problem is that the model just seems to be ignoring the important instructions you put at the end of your prompt, then the stupidly simple RA2 hack is your answer. It directly patches that architectural vision problem. And this all points to a final, really interesting thought. For a while now, getting the best results from AI has felt like you had to be a prompt whisperer, you know? But these solutions, RLM and RE2, they suggest a real shift. We're moving away from just talking to models and toward consciously engineering the data and the flow of attention. It's less about whispering and a whole lot more about architecture. Maybe we're not prompt whisperers anymore. Maybe we're becoming the first generation of true AI architects. Thanks for joining me for this explainer.